some problems still on differential calculus. And from our previous class, we looked at the differential coefficient of a function, that is, the definition and the formula for the differential coefficient of a function. And also, we looked at differentiation from the first principle, that is, how to differentiate using the first principle. Then also we looked at some rules of differentiation, some rules of differentiation. And under this, we have some rules like the sum and product rules. We have sum and difference rule, we have the product rule, we have the quotient rule, then we also have change rule, which is a derivative of function of a function under this. So if you want to look at the videos we've done under this, you can check our previous live class to see all this one. Now, in this class, let's solve some problem still on differentiation before we move to the next thing under this particular topic. Now, find the slope. Example, find the slope of the following curve at the point indicated. So the first one, we have this curve, y equals to 3 plus 2x minus x cubed over 3. This is at point x equals to 0. Now let's solve this first. So the slope that we are finding here is same thing as the derivative, because the slope of a curve is a gradient of the tangent to the curve. So that's the definition of differential coefficient, which is known as the limit as delta x tends to 0 of delta y over delta x, which is same thing as dy dx. So here we have that slope we are finding here is same thing as the differential coefficient, which is same thing as this gradient of the tangent to the curve, and also we can call it the derivative of y with respect to x. Now here we want to find dy dx at point x equals to 0 here. Now first, when we differentiate this, dy dx of a constant is 0 there. That means the dy dx of 3, that's 0, plus differentiate 2x, that's 2 with respect to x. Then differentiate, here we have x cubed, that will be minus 3x squared over 3. Now the process here, we multiply the power and the coefficient. The coefficient here is 1, then we subtract 1 from the power. So that's standard derivative from standard derivative. Now here we now have the y dx here is now equals to 2, because 0 is nothing, so 3 cancel each other here, and we have 2 minus x squared. Now at point x equals to 0 here, it implies that we substitute 0 for anywhere you see x, so we have dy dx at x equals to 0 is now equals to 2 minus 0 squared here, which is 2 minus 0, which is equals to 2. So the derivative or the slope of this particular curve at point x equals to 0 here is equals to 2. Now let's look at another one similar to this. Number 2 question here. We have y equals to x squared plus 3 over x at x equals to 1. Now, in the same way, we have to find the slope of this curve at x equals to 1. Now, the slope here, which is also the gradient or the derivative or the differential coefficient, which is dy dx now, will now be equals to differentiating x squared, that's 2x. Then here, we can, before we differentiate, we can even write this again from what we have. We can say this is y equals to x squared plus what we have here, same as 3x raised to power minus 1. Because here, when we have 1 over a raised to power n, this is same thing as a raised to power minus n. So that is that. Then here, we can then differentiate and we have the y dx from here will now be equals to 2x here. Then minus 1 times 3, that's minus 3. Then x raised to power minus 1 minus 1, that's minus 2. So we have the derivative here. Now, at x equals to 1 now, so dy dx at x equals to 1 will now be equals to 2 into bracket 1 minus 3 times 1 raised to power minus 2. So that there become dy dx now equals to 2 times 1, that's still 2, then minus. Here, what we have here will still be 1. Because when we have this as 1 raised to power minus 2, following this, what we have here, you can see this 1 over 1 squared. Because this negative here is serving as the reciprocal. So this is t1 over 1, which is t1. So what we have here is 1. So 1 times minus 3, that's still minus 3. So therefore, dy dx here at x equals to 1 is now equals to minus 1. 2 minus 3 there, that's minus 1. So you are watching Master T Math class, and thank you for joining us. We are looking at differential calculus in this class. So we have done some videos in our previous live classes on this same topic. You can as well check them and do it to subscribe for access to our upload at any time. And thank you. God bless you. Now let's look at the third one under this particular example. Here we have number 3, y equals to 8x minus 3x cubed at x equals to 2. Now, also we find the slope of this curve, y equals to 8x minus 3x cubed at x equals to 2. Now, the slope we are finding is same thing as the y dx. Then, when we differentiate this function now, derivative of 8x, that's 8, then minus. Derivative here we have 3 times 3, that's 9. Then x raised to power 3 minus 1, that's 2. So now at x equals to 2 here, it means we have the y dx at x equals to 2. This will then become x minus 9. Sorry, we have 8 here. 8 minus 9 times x now, which is 2 squared. Then this becomes 8 minus 9 times 2 squared, that's 4. Then that means we have 8 minus 9 times 4, that's 36 there. So when we subtract here, we have minus 28 from here. So which implies the slope of this curve at x equals to 2 is minus 28. So that is how to find the slope of a curve at a given point. And thank you. So give a thumbs up to show you are following us in this class. Now, before we go to the next thing here, we have a very important thing we need to know under differential calculus as well, which is called higher derivatives. So higher derivatives. Now, from the word higher derivatives, here it means we have derivative in different order. Now, for instance, we can have nth order derivative of y with respect to x. So nth derivative of y with respect to x, we have d raised to power n y over dx raised to power n. So this is the formula where n here starts from 1, n starts from 1 and so on. Now the first order, so n could be 1, 2, 3 and so on, depending on the order we want to examine. Now for first order derivative, first order, this will be n is 1 here. So first order implies we have dy dx. So dy dx here is a first order derivative. Then for second order derivative, for second order, we are going to have n to be 2. So we have d square y dx squared. So for third order derivative, we are going to have d raised to power 3y and the x raised to power 3. Now, this is, higher derivative and so on and so forth until we have, to where we are going. Now, what is important here is that the second derivative here is derived from the first derivative. That is, here we have this is same thing as d dx of dy dx. That is, when this multiply here, it will give us what we have here back, which is d square y dx squared. So that is that, which implies we can get the second order derivative without first calculating the first order derivative. And the same way, the third order derivative is derived from the second order, which means we can't get the third order without first getting the second order. So this same thing as d dx of d square y dx squared, which is also same thing as d raised to power 3y over dx raised to power 3. So for us to get the third order derivative, we should get the second order derivative first, and so on and so forth. Now, here, let's look at one example to demonstrate this. Now, find the first, second, and third derivative of, example here, find the first, second, and third order derivative of y equals to 2x raised to power 4 plus 3x squared minus 4. Now, from what we are given here, we first find the first order derivative from what we have. That is, here, the first order derivative first order, which is same thing as dy dx, will then be equals to here, when we differentiate this now with respect to x. So here, 2 times 4, that's 8. And subtract 1 from, the power here, that's x raised to power 3 now. Then plus, here 3 times 2, that's 6. Subtract 1 from the power, that remains x raised to power 1, which is x. And derivative of a constant here, which is 4, that's 0. So here we have the first order derivative. Then the second order from here, this same thing as the square y dx square, which implies that we differentiate the first order to get the second order. Now, from here, differentiate the first order here, which implies that we have 8 times 3, that's 24. Then subtract 1 from the power, that's x squared now. Then plus here, this becomes 6. So this is the second order. Then the third order as well, which is the d raised to power 3y and the x cube. Here we differentiate the second order. So this here, 24 times 2, that's 48. Then subtract 1 for the power, 48x. Derivative of a constant here, that's 0. That means the third order is 48x. So we have the first, the second, and the third order derivative here. So that is what we mean by the higher derivative now. So let's stop here for today. So next class, we are going to solve more example here and look at another aspect of differential calculus, which is implicit function, derivative of implicit function. So subscribe in order not to miss out, and then thank you. We appreciate you for joining us and see you next class. Bye for now.